Hello and welcome back. Today what we're going to start talking about are dilations as we enter our unit on similar triangles. So far we've talked about several transformations, a translation, a reflection, and a rotation, and the final one that we're going to talk about is a dilation. There's actually one more which we call a glide reflection, but it wouldn't be anything new. It would be the combination of two of them that you've already done. So as we look at this example, what we're going to focus on today is actually how do we construct the dilated image using our construction tools. So I sort of highlighted some of these words that we see in our picture. Construction tools being a compass and straight edge, and we want to create a scale drawing of the original triangle ABC with a scale factor of r equal 2. So a few things that we might not quite understand would be the scale factor of r. And so a scale factor is any length in a scaled drawing relative to its corresponding length in the original figure. And we know the original figure is really our pre-image. So we bring back some of the vocabulary that we're using. And then the resultant is the image. And so what this scale factor is, or the r, it's equal to the image, or the result, divided by the pre-image. And so this is going to be quite an important ratio for you guys. And it's basically saying that if I took a ruler and measured, I could set up a division problem and get to the value that is r right here. And so there's a couple ways to look at this. I'm going to show you the easiest way, and then I'll show you a little bit more developed way to be able to find the dilated image with a scale factor of 2. And so probably the easiest way is to look at this and just extend the side lengths of CA and the side lengths of BCB. You don't have to go from the angle C. It's just the one I'm going for, and I could do this the same way. I could extend BA here, and I could extend BC up this way. I just figured I'd hit the writing, and I didn't want to do that. So I'm working down. And then really basic is if I'm supposed to double this for the scale factor of 2, that's what it's saying is that I have to double it. I just have to mark off two distances that are equal to CA. So here's one, come down, and here's another. And so this will give me the value, or the spot, the point where I have A prime. I can do the same thing for CB. Come down, mark that distance off. And now this will give me B prime, and then just connect the two. And you might be wondering, how do I know that this is going to be the correct way? And similar to the way we do triangle congruencies, we also have similar triangles with a side, an angle, and a side, as long as the sides are in proportion. And so if I look at this, I get my ruler out, I know that CA is approximately 2.5 centimeters, and then if I look at C A prime, I'm just underneath 5. I'm at 4.9, and that's why this was just a bit smidgen short. And then if I do the same thing for CB, so remember this was just under, so like 2.45, and then this was 4.9 centimeters. Over on CB, I look at it, it looks like it's just underneath 3.5, which means I should have something that's just underneath 7, which I do. And then the whole thing is centimeters. And so if I were to compare these ratios, 7 divided by 3.5 should equal 4.9 divided by 2.45, and that should all equal 2, which ties back to my ratio. And so that's just a simple way of dilating something if you've been given the image and you can work from it. The other way you can do this is you can actually construct this all by yourself using angle copy. And so what I'm going to do is I'm going to bring a line all the way here on the left. Just have to make sure it's double the length of A. I'm going to label this with A. And what I'm going to do is actually I'm going to find the distance B. Okay. And so again, what we do is we mark off B. And so now I can find B prime. So here's B prime. And then I'm kind of stuck because I really don't know exactly where C would be relative to the points A and B. But it'd be awesome if I could replicate this angle from B to C and have like this big long line here, and then do the same thing from A and have a big long line, and where they intersected, that would be the point C. Well, we do know how to make an angle copy. And so what you do is you come over here and you just mark off one circle. And you find one other, so I'm going to take my compass, wrap that around again at B, and then I just need to match that distance. So I come over here to point A, and I give myself one other arc. And so this should be the angle I need to figure out C. And then I mark the same angle. It's an angle copy. I'm going to come down here. I'm at B. Oh, sorry, A. I marked off a distance. And the importance of this distance is so that I can have two exactly same distances. And so I look at A, mark that distance off. And then I just need a corresponding point on that arc to then come up here and mark the line off for C. And so boom. And what you're going to see is that when I connect this, this triangle should be almost exactly what I reproduced over there. And you can see that they look pretty similar. And then you get out the ruler because you're a skeptic, and you see that this is approximately a little bit bigger than 5 centimeters. It's a smidgen off. It's a little more variable. And then this was supposed to be 7. And so this is just about 7. And so that's how you can use angle copy to do the same dilation. Obviously, the more times you're rotating your compass around, the more human error that can become involved. And so just one more example showing you that I didn't have to go with this top angle. You could go anywhere. So I'm going to move this out this way, and really briefly, you just extend the lines all the way out. And then you just take your protractor, you measure the distance from D to F, and since they want 3 of them, there's 1, there's a second, and now I'll have 3 total. And so this is going to be F prime. And then I go from D to E. once, twice. So this must be E prime, and connect the two. And so now this length should be 3 times what EF is. Let's just verify that. So EF is about 2.7. And so 2.7 times 3 is 8.1. I've nailed it exactly. Okay, so we did that first part. We scale factor of 3. It says, what properties does your scale drawing share with the original figure? So I'm